Okay. 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 So let me start this part on dynamics. So basically we start with differential equations. It's all the first two topics, which is basically the growth, the constant growth, and the growth towards an upper limit, which is the content of these slides. And the second topic, which is a more general view on first order linear differential equations, are relatively easy. Okay, so there is not, mathematically there is nothing difficult except knowing the properties of the exponential function. So nothing really difficult. But the only, let's say, new thing, not difficult, but new thing is somehow the perspective. Okay, it's the perspective on modeling dynamics using functions to express the time evolution of a variable in continuous time. It will also be possible to express the evolution in discrete time, which is the topic called difference equations. And we will see something about that. But continuous time is the setting, the modeling framework, which is used most often, okay, in economics, especially in environmental economics. I mean, macroeconomics uses discrete time as well, but as far as I know, environmental economics uses continuous time modeling, okay, in general. So what is, I don't want to introduce the bridge between discrete time and continuous time, but we will see in the introductory slides two examples of two problems that are written formally as problems of intertemporal optimization in continuous time, okay? We will see very simple examples at the end of the course of these problems because the main point here is being able to solve differential equations, okay? But the other important point is that you understand the structure of these problems, so the meaning of the elements that appear in the statement of the problem, because only in this way you can then interpret the solution properly, okay? So my first introductory slide that I write here is about two equations that will appear in the next slide. Morning. So suppose that you have a variable which you want to model in continuous time. So you denote it by x of t. So this is a stock, okay? The stock of a given variable time t. Suppose that this variable, this points to a classical problem in intertemporal optimization. This variable is the amount of your resources in the sense of wealth, okay? Wealth of a nation, I mean, of a country, or personal wealth, okay? And this is the amount of wealth at time t. Suppose that you want to model the evolution of your personal wealth, which depends on the wealth that already exists in your bank account, and in each period, at least in the past, there was a kind of interest rate, okay, increasing the amount of the wealth in your bank account. But there are other reasons why your wealth changes over time. One is that you withdraw part of your wealth for consumption, okay? And the other reason is that there are wealth inflows due to, for instance, a wage, okay? So these are the three main elements. There is something that decreases your wealth and something else that can increase your wealth. the interest rate applied to your existing wealth and the wage, okay? And you want to model things in this way. So basically, you are at time t. The wealth at time t plus delta t, where delta t can be 1 month, can be 1 day, 1 week. In principle, it can be also 1 year, but remember that we are trying to build a model that works in continuous time. So basically, our delta t is something that is short, very short time period, and then it will tend to 0, okay, in the limit. The wealth at time t plus delta t is equal to the wealth at time t. For instance, the wealth at the end of the month will be the wealth at the beginning of the month. Plus, okay, so plus consumption, sorry, minus, because this decreases the wealth, minus the quantity which is consumed from time t to time delta t to delta plus delta t, okay? And this is modeled in this way. Remember that in continuous time we have flows. So this is the intensity of the flow of consumption multiplied by delta t. I mean, all of these symbols have a meaning. If this is the intensity measured in quantity consumed per year, and delta t is 1 over 12, 1 month, okay, your monthly consumption is Ct times delta t. So Ct divided by 12, okay? And this is something that decreases the wealth, plus interest rate times existing amount of wealth times delta t. Typically, the interest rate is per unit time. If you want to compute the interest, you have to multiply the interest rate by the amount of the capital, which is your wealth, by the length of the time, okay? The interest rate is annual. So this is the interest that increases your wealth from time t to time t plus delta t. And finally, if you like, this is already enough to model for our model, but in principle, there can be other sources of inflow of wealth, okay? For instance, plus the wage, and again measured by an intensity times delta t. So if this is the annual wage, you have to multiply it by delta t, where delta t is the length of time measured in years. For instance, 1 over 50, which is 1 week, okay? So basically, this is the time evolution of the wealth. Now, see what happens. Move this to the left. So this is a model in principle in discrete time, which can be understood very easily, okay? Now, move this to the left. This is the change of your wealth. And express the change of your wealth per unit time. So divide, once you move this to the left, divide it by delta t. So what is left on the right-hand side is R xt, because you divided by delta t, minus Ct, and possibly plus Wt. Okay? Possibly plus Wt. Now take the limit as delta t tends to 0. Assume that in your model, these kind of functions are sufficiently regular, so you can compute the derivative. If you take the limit as delta t tends to 0, what is this one? This becomes the time derivative of your wealth, okay? This becomes a time derivative of the stock of your wealth. The time derivative, which is called fully displayed is like this, but with short notation, it is x dot, time derivative, is equal to Rx. Often we omit the argument of the stock variable, Rx, which means R times xt, minus Ct, and possibly plus Wt. Okay? So this is an example of a state equation. This is the equation that represents the evolution of a variable that typically represents a stock You will see later another example with a stock of a natural resource in the next example. A stock variable typically is the variable involved in a state equation. It is a dynamic equation, and it is basically an example of differential equation, okay? So the time derivative of your wealth depends on the existing level of your wealth times a parameter, which is the interest rate, minus the amount of your wealth that is consumed in a short time period, okay? Plus possibly the wealth inflow in the same short time period, okay? So this is an example of a state equation. So what is the problem here? The problem here is that in this kind of models, in the most sophisticated, let's say, use of dynamics, which is dynamic optimization in continuous time, typically, this is an equation that describes something that happens, okay? But this is a decision variable. This is also a kind of given data, so you know what your wage is, so you model your wage. But this is typically a decision variable, okay? This is a decision variable. You want to maximize, let's say, the amount of wealth at some terminal time, and the wealth evolves in this way. It increases due to the interest rate, it decreases due to consumption. Possibly there is another exogenous inflow, which is the wage. And you have to select C, okay? Now, the first answer would be, okay, if I want to maximize the wealth, I don't consume at all, okay? If C is equal to 0 at each point in time, of course, your wealth only increases. It never decreases. So it's likely that the final amount is highest as possible. But you will see in the next slide, we want to constrain our wealth to have some minimum level at the end, but at the same time, we want to maximize the utility from our consumption over the given time horizon. So the point is that we have to consume something, and the decision is between consuming, for instance, a constant quantity all over this period, or a quantity that increases over time, or a quantity that decreases over time. So we have to find the optimal path of consumption over time in order to maximize some function of the whole consumption trajectory. But at the same time, we have very clear in our mind that the wealth evolves in this way. And if we consume too much, we may not reach our final constraint to have our final wealth at a given level, at least at a given level, okay? So this is very typically the structure of a problem, you will see in the next slide, and this is the state equation of this problem. A state variable increases and depends both on some natural forces, the interest rate and the exogenous inflow, some exogenous forces, and on our decision. So our variable changes depending also on our decisions, okay? And this is one example. So let me show you what is the fully displayed problem. A problem of optimal consumption has this structure. We have to maximize, you see here, an integral, okay? The integral between 0 and capital T. Capital T is our time horizon. The interval 0, capital T, is our time horizon. For instance, 10 years, 20 years. Possibly, T is plus infinity, okay? Because we just want to maximize something that will also involve, let's say, the next generation. So, I mean, it's to plus infinity. Also, in general, plus infinity is very important in applications to, for instance, to environmental economics, okay? Because you have to, your time horizon must not end. But look at the structure. Ct is the quantity under our control. We derive some utility from Ct, and this utility has the usual properties. It is a very simple function which is increasing and concave. Increasing and concave in economics just means that more consumption is better than less consumption, increasing. But if you already consume 100 and you increase your consumption by 2, you have a smaller effect on your utility than if your consumption is 10 and you increase by 2, okay? It's concave means an effect of saturation. Increasing, for instance, square root of C could be a reasonable utility function. But look at this. This is a discount factor because I might postpone consumption to, let's say, 10 years from today, but I must be careful because consumption in the future is worth less than consumption today, okay? So it is discounted. The utility of consumption is discounted. And this is an integral that aggregates all the instantaneous utilities at each point in time over the time horizon. It aggregates these quantities and it computes a kind of present value today. So, in order to, since it is increasing, in order to consume more, in order to have a higher utility, I could increase consumption. If I increase consumption, utility increases and also the sum of utilities increases. But the point is that if I want to finish with a given, for instance, a given wealth at the end, I cannot consume too much, okay? Because otherwise my wealth will not reach the target level at the end. So it's a trade-off, basically, okay? It's a trade-off, which is typical of economic theory. We have resources that are scarce and we have to employ them optimally. So this is called flow consumption. This discount rate need not necessarily be an interest rate, a market interest rate. It is called subjective discount rate because it depends also on the time preferences of the decision maker, okay? But and it is different from the market interest rate that appears in the state equation, okay? So this is a true market interest rate. This is a subjective interest rate. The utility has these properties. This quantity to be maximized is not really a function. It's because the decision variables. What are the decision variables of these problems? When you have a function of one variable and you want to maximize it, you have to select the values of x that maximize your function, okay? So your decision variable is x, you have a domain of choice, you select one value in the domain. What are the decision variables here? Each possible path of CT over time is a specific value of the decision variable, okay? So you have to select, optimize by selecting among all the possible time paths of the consumption. So the decision variable is a function of time, okay? And next there is a state equation already described before, the exogenous income flow, the state variable, and capital X of t is determined by the boundary conditions. Boundary conditions can be of different types. In this type of problem, it makes sense to set a minimum final level for the wealth. So the boundary condition in this case would be X at the terminal time be greater or equal to some given level, okay? Another type of boundary condition is equal to. I want to impose equality of the final wealth to some given level, equality constraint. And there are also problems in which we don't specify the boundary condition, which is not, it's not very realistic here, okay? There are also problems in which we don't specify the boundary condition. So it's called a free endpoint problem, okay? Another problem of this type, you will see that the structure is the same, is a typical structure of a problem of a renewable resource, which is called the Fisher problem. You see here, we have very typical quantities, and I don't describe the equations again. They are in continuous time, they involve, but it can be derived from our discrete time, okay? What happens in the next month, okay? And then let delta t tend to 0, the structure is the same. The stock of a given resource, for instance, the stock of fish, is called S of t, okay? So let's look first at the state equation and then try to understand the optimization problem. The stock of fish is S of t. Of course, the stock of fish evolves naturally due to some law, natural law, because there is, of course, the increase of the stock of fish depending on the environment, of course. So typically, we could assume naively that the stock of fish increases proportionally to the existing stock of fish, But in natural sciences, this is not actually the case because there are also environmental constraints. So we use in general another kind of growth model, which is called logistic growth. And logistic growth means that, okay, there is a rate at which the stock of fish increases naturally, but the closer the existing stock of fish is to some upper level, which is called carrying capacity, the closer the existing stock is to the carrying capacity, the smaller is the rate of growth of the stock of fish, okay? But in principle, we have a function by which the change of the stock of fish is related to the existing level of the stock of fish. In the most simple example, that could be a constant time st, as in the previous example of the interest rate, okay? But in general, it is more complicated for natural resource modeling, okay? It is a logistic growth model in general. And minus what? The stock of fish depends also on the rate of harvesting, okay? And this is the decision variable. How much fish is it reasonable to harvest per unit time, okay? It's called, the intensity is called h of t, harvesting, okay? Harvesting rate is the control variable. So our stock of fish increases naturally, but can be reduced by our rate of harvesting. We may build very simple models in which we just assume that the rate of harvesting must be some fixed parameter, h, and we have just to select the level of h. But in dynamic optimization, it may be reasonable to assume, for instance, that it is optimal to harvest less at the beginning of the time horizon and more at the end of the time horizon, or vice versa, depending on a lot of factors, okay? So we leave this free as a function of time to be selected, okay? We want to select a trajectory for harvesting. Now, there may be other possible constraints. For instance, the harvesting rate cannot be a negative quantity, can be zero. I mean, I cannot. So in principle, negative quantity would be adding new fish, okay? So it goes from zero to some, for instance, maximum level, h. These are possible types of constraints. There are many variants of such problems. The initial stock of fish is zero, is the stock that we observe today. And we want to end with a given stock of fish, okay? So this is a constraint, so this is an objective also of the decision maker. We want to maximize our harvesting by ending with a given stock of fish, okay? Selected in advance. So what is the main message of these problems? Usually we have state variables that are stocks and control variables that are flows. You see here, the control variable is h of t. Okay, so the optimal policy would be, let's say, without taking into account the constraint, would be to increase harvesting, right? But then you have to sell harvesting, the quantity harvested on the market. So the quantity harvest in a time period of length dt is ht dt multiplied by the price at that point in time. This is the revenue. But of course, also here we are discounting because the revenue in the future is worth less than the immediate revenue. So this is maximizing the revenue from harvesting over the given time horizon, but taking into account that the stock of fish grows, so it's renewable because it grows here endogenously, okay? Grows endogenously, and then can be reduced exogenously by your intervention in harvesting. But you have to end up with a given stock, so you cannot harvest as much as you like, okay? This is a problem. So again, here you see a trade-off. State equation depends negatively or positively on your intervention. Typically, the state equation must end with a given value, and the effect of your intervention in the objective function is the opposite than the effect that you have in the state equation. Okay, so here state equation decreases with harvesting, but the objective increases with harvesting. So it's a matter of trade-offs. In the previous example, the state equation decreases with consumption, and here it increases with consumption, the objective function, okay? You may have other examples in which the state equation increases with your intervention, for instance, the investment flow, but the investment has a cost, okay? So the objective function must be minimized, okay? Because your investment is a cost, okay? So basically we have models in which we have a trade-off between what we have in the objective function and what we have in the state equation. This is not called objective function, but objective functional, because it is not really a function of one variable. This is the objective functional. Okay, so this is the initial description. Now we focus on these type of equations that describe the state, the evolution of the state variable, okay? So we want to solve this equation for a given initial level and assuming and making assumptions of CT. Then I will show you examples in which CT, or the control variable, can be chosen optimally. But now we make different, let's say, scenarios for CT, and we see what happens to the evolution of our state variable. This is basically studying differential equations of the first order. Okay, so the very basic example is, the so-called constant growth model, but it is the properties of the exponential function, basically. So I will go very quick with this basic model. And you can look at your textbook. It's very well written in this part. What is a differential equation in general? The differential equation is an equation like this, in which you have a function of time, x of t, which is unknown. So you don't know what is the path of this function of time. And you have to find the path of xt by solving the differential equation. It is unknown. It relates the time derivative at some point in time to the value of the function and to some other factors, okay? But you don't know what is the path of xt. You have to find the path by solving the differential equation. Since we start from a derivative, solving is also called integrating, okay? So the integral is basically the solution of the differential equation. So we have differential equation is called differential equation because the derivative or the derivatives in more difficult models, the derivatives of unknown functions x of t appear in the equation. And they are equations because the trajectories of our variable xt are basically the unknowns of the equations. In algebraic equation, the unknowns are numbers, okay, to be determined by solving the equation. Here we have functions to be found by exploiting a property that relates the derivative to the level of the function itself. Time t is most often the independent variable. So in dynamics, of course, the independent variable is time t. So the unknown functions are functions of time. But in general, in mathematics, a differential equation need not be defined in a way that the independent variable is time. It could be any meaning, okay, or just a formal equation. The basic model, okay, let me just start with this. What is the simplest type of differential equation? It's a computation of an integral, a simple integral. Because suppose that you have a function which is a function of time, and this function is unknown, okay? You know its derivative, and you know a relation between its derivative, time, and possibly the level of the variable. Here, the level of the variable is absent on the right-hand side, but this is a particular case. The derivative, x dot t, is equal to f of t. This is the simplest possible type of differential equation. In fact, we don't need the theory of differential equations here. By definition, this means finding all the functions having ft as their derivative, okay? So the solution is the indefinite integral of our function, okay? So basically, we can also write this in this way. This is not really correct notation. It's capital F of t, any primitive, plus a constant. Okay, so this is the basic model. But let me introduce the terminology that we use for the differential equations. This is called the general solution. We know this is the indefinite integral, okay? In the language of differential equations, this is called the general solution. From the general solution, if we impose some initial condition or some boundary condition, we can single out particular solutions, okay? So in the language of differential equations, the equivalent of the indefinite integral is the general solution. If we impose some additional condition to single out one particular function among the set of all the possible solutions, we find a particular solution, okay? This is in the language of differential equation. So the first example is really just to bridge, to set a bridge to first bridge to integrals. Here is another simple model. It's called constant growth. It's different from the previous one because here we have x dot equal to a function of time stop. Here we have x dot over x, which is the time growth rate, is equal to some, in general, function of time. Here it is constant, r. Why is this different? Because this can be written in this way. X dot is equal to r times x. Okay? So basically, on the right-hand side, we not only have a constant that in principle could be a function of time, could be r of t, if this parameter changes over time. But we have also the level of the function, so it's conceptually different from the previous model, okay? So here, we cannot just integrate, because in order to integrate, we should have here something that depends only on time, but now it depends only on the unknown, x. So we need another technique. Let me start with, we already know how to solve this problem, so let me start with what we already know to be the solution to this problem, okay? This kind of, we know that the exponential function, exponential of t, has as its derivative, exponential of t itself, okay? So if you compute the derivative divided by the level of the variable, you get 1. It is among the cases described by this model, okay? So one function having the ratio between the derivative and the level of the function constant and equal to 1 is exponential of t. So this is 1 among the solutions if r is equal to 1. Now, take this other function, slightly make this basic function more richer, okay? 3 times exponential of minus 2t. Compute the derivative. The derivative is 3 times minus 2 minus 6 exponential minus 2t. Take the ratio between the derivative and the function. It is minus 2. Okay? So it satisfies x dot over x equal to minus 2. R is equal to minus 2. So we are very close to our general solution because clearly if you have an equation of the type x dot over x is equal to a constant, and you try with a function of the type another constant, any constant, times exponential of rx, or rt, sorry, rt, you have one solution. Okay? So basically, the question is, we are just trying different possibilities. So the question is x of t equal to a constant times exponential of rt the general solution to this problem? Which means we know that these functions satisfy the differential equation, so they are among the solutions. Does this describe the whole set of solutions? Are there any other functions not included in this class that satisfy the equation? Is this the general solution? And in general, this is the most difficult problem, theoretically, okay? So we can find some solution, but it's difficult to find a whole set of solutions to a differential equation in general. In this case, it is possible. Okay, so we know already that any function of this type is a solution. How can we prove that this is the set of the general solutions? And this technique, this is one of the cases in which I suggest the proof, because this technique is not useful only for the proof of this one and other similar problems. It's a technique which is called the technique of the integrating factor, which is used for a lot of problems in the solution of linear differential models, differential equations, okay? This technique is called technique of the integrating factor. Here is an example of a very simple application of this technique. And the required background to understand the technique is to understand, to remember what is the derivative of xt, where x is a given function of time, times exponential of minus rt. Okay? It is a product. So we apply the product rule for differentiation. The derivative of xt, x dot t, it is the time derivative, so I can use the dot notation, x dot t times exponential of minus rt, okay? Plus xt times minus r times exponential of minus rt. So this is the derivative of our xt times exponential of minus rt, which is our unknown function, times exponential of minus rt, where r is the parameter that appears here in the differential equation. It has this expression, and you can write this as, for instance, x dot exponential minus rt minus r, x exponential minus rt. So you don't need to specify the time dependence of your unknown function, okay? Remember this, and now apply the integrating factor method to prove that these type of functions constitute a whole set of solutions. You have your differential equation. Xt is an unknown function. We want to find all of them, okay? X dot t is equal to r times xt. This is the differential equation. Of course, we are assuming here, okay, this is our differential equation. This one, right? X dot is equal to rx. By the way, this is the differential equation. If we write this in this way, we must assume that x is different from 0, which is another additional detail to be discussed later. We start with this differential equation, which implies constant growth, constant time growth. You remember the time growth rate of a variable? It is the derivative divided by the level. It is the logarithmic derivative of the variable, okay? Okay. This is our differential equation, and this must hold for our unknown function t for any t. Multiply both sides by exponential of minus rt. Both sides. Okay, x dot exponential minus rt, and on the right we would have rxt exponential of minus rt. Move this to the left, so we have minus rxt exponential of minus rt equal to 0. Okay? Now, on the left-hand side, we have the derivative of xt exponential of minus rt, which is the previous slide. This is the time derivative. So we transform the problem in which the unknown is the derivative of our function. Our function is xt, to a problem in which our unknown function is xt to the power exponential minus rt, okay? So this is the derivative of xt multiplied by exponential minus rt. But if a function has a 0 derivative, this must be identically 0. If a function has a 0 derivative, it must be a constant, okay? Necessarily, this is a basic theorem of calculus. Any function having a 0 derivative on an interval is a constant. We don't know which constant, but it is a constant. So we know that xt, exponential minus rt, is a constant. This, by the way, this can also be 0, okay? This constant can also be 0. And this means that xt is equal to any constant times exponential of rt, where a is any real number. So basically, this is the set of all the solution, all the possible solutions to our problem, which is exactly what we conjectured initially, okay? Although this is intuitive for this function, but keep in mind the technique we use to solve basically We use this technique to solve the equation. Okay? This is called integrating factor technique. It is very useful because it can be applied, for instance, also to a situation in which R is not constant, but it depends on time. It can be applied in the same way. I will show you this later. So what is the basic insight here? That any function with this
Excuse me, Professor.
Yeah?
Is it multiplied? Shouldn't it be A divided if we bring it to the other side?
But divided by exponential of minus RT is multiplied.
Oh, okay, yeah. I didn't see the change in the exponent. Sorry.
Okay. The set of all the possible solutions is like this. We have two qualitatively different cases. One is when R is a parameter which is strictly positive. So basically, if you go to the basic equation, you have an actual growth, okay? The growth rate is positive. When R is positive, you have a family of functions like this, okay? So depending on what is your A, you have these paths. Remember that we are finding an indefinite integral in this case, so we have a family of functions, okay? We have this path of functions. If you start with a positive A, for instance 2 exponential of, I don't know, 1/2 t, is like this, okay? If you start with -3, it's, for instance, like this. Because it depends, so the part above the horizontal axis describes solutions with a positive A, below is solutions with a negative A. And this is the case of R positive. Okay? Anyway, these solutions, since R is positive, are multiplied by a factor that increases over time, so it moves far and far away from the horizontal axis, okay? But the case where R is a negative quantity is described here. Different starting points, depending on A, as above, but now all the solutions approach, in the long run, they approach the level 0, okay? Why? Because if you have a model of constant growth, which is a constant decline, with R negative, this means that in each unit of time, for instance, minus 0.10, in each unit of time, your variable decreases by 10% of the level existing at the beginning of the short period, okay? 10% per unit time of the level at the beginning of the period. But clearly, if you start with a positive variable, this will only remain positive, but it will decline until it approaches 0. This is the typical exponential behavior converging to 0. If it is negative, it will remain negative, but it will approach 0 from below, like this. So the representation of the time path of the family of functions for positive parameter R, positive growth rate, negative growth rate. Remember that this is an indefinite integral, like an indefinite integral. We may want to find, to impose additional conditions to single out only one time path among the infinitely many. Typically, we impose initial conditions, okay? Typically, but we don't need to impose initial conditions. We can impose a terminal condition if we have a terminal time in the model. We can impose a condition related to the value of our time path at a specific intermediate point in time. So it's general. It's a boundary condition. But in general, a boundary condition is like imposing that the curve among the family passes through a given point. If we impose that the curve passes through a given point, we are left with only one solution among the infinitely many. That should be proven in general. It's a problem of existence and uniqueness of solutions of a differential equation, but we skip this part, okay? It's intuitive that if I select this family and I impose a point here where you see the hand, the only curve passing through this point is this one, okay? So we select one among the infinitely many. So basically, let's look at this example. It's an example of constant population growth. X dot over x is equal to 2% per unit time. per year, for instance. We want to solve this problem because from our data, we want to find a model that simulates the evolution of this population over a certain time period. Among our data is the fact that at time 3, at the end of the 3rd year, the population is this one, okay? And we want to find the whole path. The first thing is to find the general solution, but the general solution is a given constant, multiplicative constant, capital A, times exponential of R, 0.02 t, okay? Now, what is A? Because finding a particular solution means finding a specific value for the arbitrary constant of integration, okay? What is A? We know that at time 3, so t is equal to 3 here. So here it becomes exponential 0.06 times A must be equal to this, okay? If you solve this, you find A, which is equal to 9 millions and etc. This one, okay? So A is equal to this one. So we have now a numerical value for A. We put this numerical value in the solution, and we have our particular solution, okay? Clear? We don't, in 99% of the cases, you will select either an initial condition or a terminal condition if there is a finite time horizon, okay? But in general, we can select a condition that imposes a level at an intermediate point in time. Now we have our trajectory, xt, the population has this trajectory, xt is 9 million and etc. times exponential 0.02 t. What is the meaning of this factor here, the specified value for A? Now, we derived our solution by imposing that the size of the population at time 3 is this one. Just we wonder what is in this model the initial population level, okay? What is the initial population level? T is equal to 0. This becomes 1. So the value for A that we found represents, in fact, the level of the initial level of the population, okay? But remember that in general, even if we will specify the constant using an initial condition, so imposing that the initial level of our variable is this one, okay? The meaning of A, the constant, will not be in general equal to the initial level of the variable. This happens only in this baseline model. So only in this baseline model, the model of constant growth, the initial level of the variable is exactly equal to the value of the arbitrary constant, okay? Only in this model. In more sophisticated models, it will be related to the value of the arbitrary constant, of course, but will not be the same thing. So this is a summary of the constant growth model. The model x dot over x equal to r, or better, x dot is equal to rx, with the given initial condition specified, called x0, has the solution x of t is equal to x0 times exponential of rt. Okay? Remember that this model includes also a very, very particular solution, which is this one. It is the red one on this axis. The solution, variable equal to 0 at each point in time, okay? Also, the time path in which our variable is equal to 0 at each point in time is among the solutions of the problem. Of course, this corresponds to the general solution when A is equal to 0. Clear? It is the only, look at the graphs, it is the only constant solutions. All the other paths are time varying, okay? But 0 is the only constant solution here. Constant solutions to differential equations like this one are called steady state solutions, okay? A steady state solution to a differential equation is a solution in which the value of the variable remains constant over time. Anyway, it is a solution to our differential equation, okay? So here we have an example of a steady state solution in the most trivial case. Xt equal to 0 for any t. And by the way, if xt is equal to 0 for any t, of course, you cannot write your equation in this way. Because x is equal to 0, you have to write this in this way, okay? Sorry, you have to write the equation, not in this way, but only in this way. In any other way, you can write the equation like this. If a variable is 0, you cannot measure the growth rate, because you can measure the derivative, not the time growth rate, okay? Because the time growth rate is a ratio with the level of the variable. Okay, so this is the basic model. Nothing. Here is already an example that introduces a very standard notation in which you see not a growth, but a decline of a quantity. And this is an example in which the variables express the depreciation of a capital stock, a stock of capital. So the general model of capital stock depreciation is like this. We have a stock, which is, for instance, the stock of capital of an economy, K of t, capital K of t. This is a stock variable. Delta is called the depreciation rate. So for instance, 3% per year, 0.03. K is the level of the capital. And I, capital I of t, is the net investment. This is a flow, okay? This is a flow, the flow of the net investment. You add new capital to the economy. So this is not a net investment, this is a gross investment, okay? What is the difference between gross and net? In order to find the net investment, you have to subtract the depreciation, so the loss of value of the existing capital stock from the gross investment, okay? So this is the gross investment minus the depreciation. The right-hand side is the net investment, and this actually is what increases the capital stock, okay? So this is a model, okay? In this model, we assume that we don't invest anything in the economy, so IT is equal to 0, so we have a model of constant growth, which is a decline actually, because the rate is negative. It is a depreciation rate, okay? So if we assume that K0, the initial capital stock, is 5,000, we want to find the path of KT, we want to find the time T it takes for the capital stock to fall to 75% of the initial level, okay? So the general solution to this model is just KT equal to constant, capital A, times exponential minus 0.03t. Okay, this is already the general solution. What about the particular solution? Here, I mean, we don't need to derive the particular solution, because at time 0, this becomes 1, and clearly A is equal to K0, okay? We already have K0, 5,000, so the particular solution is 5,000 exponential minus 3% t. Okay, so this is the particular solution consistent with the initial condition K0, initial capital stock, equal to 5,000. And the other question is, of course, just simple algebra. It's just meant to show you one particular property of these solutions. Of course, the time t it takes for the capital stock to fall to 75% of the initial level, if we don't invest anything, is something that doesn't depend on the initial level of the capital stock, okay? Just to show this property. It depends on the rest of the model, but not on the initial level of the capital stock, because it measures in a percentage manner, okay? 75% of the initial level, whatever it is. Okay, so we just have to find out, once we have found the solution, at what time t the stock variable will be equal to 3/4 of the initial level. the time t, the capital stock at time t is this one, 5,000 exponential minus 3% t, must be equal to 3 over 4 times 5,000. We can eliminate 5,000 on both sides, so the initial level doesn't matter for this problem. So minus 3% t is equal to the log of 3 minus 2 log of 2, okay? Could be the log of 4. So t star, our time will be this one, which is basically 9 years and 7 months, okay? So this is just to show you that in principle, since the growth is exponential, if you want to find out specific levels of the independent variable, okay, corresponding to some level of the solution, you have to switch to logs, of course. And also, by the way, what about the computation here? This is also useful to, suppose that you don't know how to solve this equation. Falling to 75% of the initial level means losing 25% of the value, okay? If it decreases of 3% per year, 25% of the value, 24% of the value would be 8 years, okay? So I would say more than 8 years. But if I solve the problem, I find 9 years and 7 months. So reasoning linearly underestimates the result. Why is that? Because if I multiply 0.03, if I try to solve the problem naively and multiply 0.03 by 7, it is 0.21. By 8, it is 0.24, okay? By 9, it would be 0.27. So it is between 8 and 9 years, okay? No, I just underestimate the result. Why is that? Because this is not a linear decline. This is an exponential decline. So the decline, it's leveled off. The closer I get to the axis, to the x-axis, and my decline in absolute term is leveled off. Okay, by linearly would be like this. Okay. Look at the representation here. If you subtract a constant quantity each year, you have a linear decline of a variable, okay? You start from 5,000, you subtract a given quantity each year, you have a linear decline. At some point you get the level 0, so the capital stock, there is no more capital stock. Or if you want to get to the level of 75% of the original level, a linear decline is like this, but an exponential decline is like this, okay? So it is leveled off. I mean, the picture is not really good, but it is leveled off compared to the linear decline. And the reason is that when you subtract 3%, you subtract 3% of a smaller quantity, okay? When you subtract 3% in a linear decline, it is the 3% of the initial amount. With the exponential decline, you subtract the 3% of the amount at the beginning of that particular year. So the total absolute amount that you subtract is smaller, okay? So it takes more time to reach the given level. This is the intuition, okay? This is an important of exponential as compared to linear growth and exponential as compared to linear decline. For linear growth, it is the opposite. It's 3% more compared to the existing level. But linear means it's 3% more of the initial level, okay? But if the level increases, exponential is more. But if the level declines, exponential is less. This is the basic intuition. Okay, so this is a model in which, this is just to introduce some notation applied to capital stock. Okay, so this is a new model, which is already an example of differential equation in which we don't have constant growth, okay? So a more sophisticated example of first order linear differential equations is like this. Okay, constant growth is this. And we know how to solve it. Now we have a model like this. Time derivative is equal to Rx, for instance. I don't call it R. I call it minus A. This is a parameter, similar to this, plus a constant. So we want to learn how to solve these more complicated models in which the time derivative is not just a constant multiplied by the level, but it is also plus a constant, okay? This could be positive, this could be negative. An example, of course, is this. X dot is equal to Rx minus C. Remember the initial example? The wealth level increases due to the interest rate minus the level of consumption assumed constant over time. So we want to learn how to solve these types of problems. There is also a constant. One of the most elementary examples is, it's very well introduced in your textbook, is called growth towards an upper limit. This is one particular case of this more general model. And it is related to, a slightly more rich model of the evolution of, for instance, of a natural resource. The constant growth model is unrealistic in the long run because exponential growth is unrealistic in the long run. It's clear, okay? Because there are environmental constraints. So one, resource constraints, environmental constraints, etc. There is a class of models that include a carrying capacity. The carrying capacity is some maximum level that can be reached by our variable, and the existence of a carrying capacity, which is an upper bound, the existence of a carrying capacity modifies basically the growth rate of our variable, okay? So look, for instance, at this model. X dot t is equal to, it's not R, a constant, times xt. It's equal to a constant times the upper bound, so the carrying capacity, minus the existing level of the variable, okay? So for instance, if our variable is very close to 0, which means very far from its carrying capacity, okay? It's very close to 0. So here we have just k. AK is kind of constant derivative of our variable, okay? But now the time derivative of our variable becomes smaller and smaller if the difference between the carrying capacity and the existing level of the variable becomes smaller, okay? If the level of my stock increases and gets closer and closer to the carrying capacity, and then this part becomes smaller and it affects the derivative. So the growth is leveled off depending on how close our variable is to its carrying capacity. We can also express these models in terms of growth rate, of course. This is expressed in terms of derivative, but we can also express this in terms of growth rates. Look at the model. The model with carrying capacity is just like this, okay? X dot is equal to a constant times the carrying capacity minus the level of the variable. We could express this in terms of growth rate as well. X dot over X is equal to this, K over X minus X over X. So X dot over X is equal to A that multiplies the ratio between the carrying capacity and the existing level of the variable minus 1, okay? If the level of the variable is very small compared to K, this is much larger than 1. So you have a relatively high growth rate, okay? But as long as it becomes, it gets closer to K, this becomes smaller. I mean, still larger than 1 because this remains below k, okay? Still larger than 1, but very close to 1, and the growth rate becomes very, very small, okay? So this is the model with the carrying capacity. And there is another model which is more sophisticated than this one, which is the logistic growth. So basically, this is a model with a carrying capacity, and we find trajectories like this. Okay, it starts from a level, it increases, but it's leveled off, and this is the carrying capacity, and this is x0. We find a model, a solution like this, which is clear, okay, from the equation. But in the logistic model, which is more sophisticated, you have something which is even more realistic. Here you have the carrying capacity, here you have the initial level. In the first part of the trajectory, the growth is similar to exponential like this. So the rate of growth is constant. It means the derivative increases, but then it reaches a point in which it goes like this, okay? So this is the logistic growth, this is the growth with carrying capacity, the simple growth with carrying capacity. This is considered a more realistic model to model natural resources, because actually if, but not only natural resources, the spread of a disease, a lot of, spread of an infectious disease, a lot of, initially there is a kind of exponential growth, but as long as the, there are environmental constraints come to play, the growth is leveled off like this, okay? This is considered more realistic. This is just an intermediate model to understand, okay, what's going on with these solutions. Okay, so the model with a carrying capacity, for instance, look at this model. X dot is equal to 0.15 times 1000 minus xt. Okay, so clearly the carrying capacity is 1000. The initial level is supposed to be 200. And we want to solve this trajectory, solve for the trajectory, the full trajectory. It will start at 200. We guess it will go towards 1000, towards the carrying capacity, but we want to find out the equation for the time path. So what we do is a very typical, another, let's say, trick, another method to solve these problems, which is the method of the change of variable, okay? With the change of variable, we reduce our model to one which we already know by changing the variable. If we focus, instead of focusing on xt, we focus on a new variable, ut, which is not the level of the population, but it is the difference between the carrying capacity and the level of the population, okay? We focus on the difference, the gap between our carrying capacity and the current level of the population. This is the new variable to our model. We get an equation that we can already solve. We can solve already. So if ut is k minus xt, now remember that this model is a differential model, so you have to compute the derivative of ut, okay? So the derivative of the new variable, time derivative, u dot t, is what? This is a constant, minus x dot t, okay? So u dot t is minus x dot t. Or if you like, x dot t is equal to minus u dot t. Apart from the notation, this is just the derivative of a function of one variable, okay? Defined in this way, okay? Okay? So, k minus xt in the original equation becomes ut here. The derivative x dot t becomes minus u dot t. So this means that if we change the sign to both sides, you have u dot t is equal to minus a ut. So the new variable evolves via a differential equation that we can already solve, because this is the model of constant growth. By focusing on the difference between the carrying capacity and the level of the variable, we have a model of constant decline of this new quantity, okay? So what is the general solution for u? Okay, it's minus a, it's our r of the previous model. So a given initial level not of variable x, of variable u, this is an initial level for variable u, times exponential of minus at. Okay, this is the solution of the model in terms of variable u. But now remember that u is k minus x. Replace k minus xt is equal to a times the exponential of minus at. Now solve for x. Xt is equal to k, so basically I move this to the right, this to the left. Xt is equal to k minus a times the exponential of minus at. This is the general solution to our model with carrying capacity. For instance, in our example, in which k is 1000, we would have that the level of the variable at time t is 1000, which is the carrying capacity, minus some constant a, still to be determined, okay, times exponential minus 0.15 t. Now, what is a in this model? We just have to impose our initial condition to discover what is a in this model. It is not the initial level of variable x. It is related to the initial level of variable u, okay? Because we solved the model for u. How can we find the variable a? By imposing the boundary condition. The condition says, okay, among the infinitely many solutions, find the one for which the initial level of your variable is 200. So we want that x at time 0. X at time 0 is 1000 minus a times 1. So x at time 0, as computed by our solution, is 1000 minus a, okay, equal to 200, which means that a is equal to 800. Okay, look at the structure of the way we use the initial condition. This is general. We use the initial condition by writing down basically two equalities. The first one comes from the solution formula. In the solution formula, we impose t equal to 0. So x at time 0 from the solution formula is equal to 1000 minus a. But on the other hand, from our boundary condition, x at time 0 must be equal to 200, okay? So if we combine them, we get the value for a. So usually we write this, okay? X at time 0 has some expression from our solution formula that includes the arbitrary constant, but on the other hand, we impose a value. So we find the value of the arbitrary constant, which is consistent with our boundary condition. Now, a is equal to 800, so that the solution in our case will be 1000 minus 800 exponential minus 0.5t. What is the meaning of 800? It's not the initial level of the variable, which is 200. It is the difference between the initial level of the variable and the carrying capacity, okay? In fact, if you solve this in general, you get xt is equal to the carrying capacity minus the initial deviation from the carrying capacity times exponential of minus at. You can repeat this as an exercise if you like, but it's clear that the structure is this one. So what is in general a, the value of the constant in the solution, is the carrying capacity minus the initial level of the variable. Now, remember what I told you before. Look at the value of the constant is not necessarily equal to the initial value of the variable. It is related to this. In the most simple model, constant growth, it is the same. But in other models, it is not the same, okay? Here, the value of the arbitrary constant is the carrying capacity minus the initial level of the variable, okay? By the way, this is a particular type of first order linear differential equation that we will solve in general later. So what is the solution, the sketch of the solution? Okay, we have t here, we have x of t here. The carrying capacity is at the level 1000. The initial level of our population is 200. And the solution, this one, has this property. Since the coefficient that multiplies t in the exponent is negative, what happens here? As t increases, this factor becomes smaller and smaller. Okay? So what is left in the long run is only the carrying capacity, because this part becomes smaller and smaller and goes to zero. So what goes to zero in this model is the deviation between the carrying capacity and the level of the variable. It goes to zero because our variable gets closer and closer to the carrying capacity. Okay? If you have a larger growth rate, for instance, a larger coefficient, not growth rate, larger coefficient here, for instance, 0.25, you have a similar behavior, but of course, it gets closer to the carrying capacity earlier, okay? So you see here different possible trajectories when you increase the value of parameter A, which is, could be 0.15, 0.20, 0.25, and so on and so forth, okay? That clear? Okay, so we can write here, once we have the solution, we can see very easily that the limit as t tends to plus infinity of our solution is the carrying capacity, okay? So basically, the final destination of all of these trajectories is to get closer and closer to the carrying capacity in the long run. Again, suppose that you start already from 1000. Okay? Here we started from 200. Suppose that you start from 1000. What does the equation, the solution, tell us? If you start from 1000, where is the solution? It is here. It is here. Here. This is 1000. This is 1000. We started from 200, so the initial level was 800, okay? Suppose that x0 is 1000. This part becomes 0, okay? But this term disappears, and the solution is 1000, okay? So if you start already from the level of the carrying capacity, the behavior predicted by the solution is that the population will remain stuck at that level, okay? This is another example of a steady-state solution to a differential equation. It's a constant solution. So if x0 is equal to the carrying capacity, the derivative, you can look this, you can see this also from the differential equation. If you start x0 from the carrying capacity, this is 0, so the derivative is 0, and it will remain 0 forever, which means that your trajectory will remain constant because its time derivative is 0. It will remain constant at the initial level. So basically, you see here an example in which a constant solution to the differential equation is x equal to k. In our example, x equal to 100. This is another example of a steady-state solution. So for instance, what happens? I mean, it makes full sense to start from below the carrying capacity, but what about starting above? Suppose that you have already a very large level of the population, okay? A very large level of the population, and you inject additional stock here, and you, in a way that exceeds the carrying capacity. What happens to our equation? If you start from 1000 and 500, for instance, this becomes minus 500, okay? Times 0.15, this is negative, so time derivative is negative, okay? So you will have a variable that decreases until it reaches again the level of the carrying capacity, okay? Clear? Okay. Okay, this is another example similar to the previous one. After how many years will the population be equal to 700? It's the same solution method as above. I don't want to comment on this. It's the same problem, okay? And here we have an alternative solution strategy, and just this one. This is, let's say, not 100% rigorous, because we should discuss more things, but it is quite intuitive. So an alternative solution strategy for the constant growth model is like this. You have a constant growth model. So this is again constant growth model, okay? So no carrying capacity here. I want to show you this because it is related to calculus and the log derivative. X dot over x is equal to r. We know that x dot over x is not the derivative of x, but it is the time growth rate of x. That is, it is the derivative of the log of x. So we know that the derivative of the log of x, you can, please don't consider, I mean, in general, we have to consider the log of the modulus of x of t. But suppose that we are dealing with positive quantities, okay? So the log of x has a derivative which is equal to r. So I can integrate here, okay? Because if the derivative of the log of x is equal to r, this is a new function, y. The log of x is y, y of t. Its derivative is equal to r. Our function, y, is, compute the integral, r times t, plus a constant, okay? But this is not the solution. This is the log of our solution. Since this is the log of our solution, if we want our solution, we have to consider this as the exponent. So we have the exponential of rt plus c. Okay? The exponential of rt plus c is the exponential of rt times exponential of c. This is a constant, a multiplicative constant. So b times exponential of rt. In general, since we may have also functions that are negative, this reasoning, this line of reasoning must be applied to the modulus of our solution, which in particular leads to this solution formula, in which the constant can be any positive or negative value, okay? So this is another alternative way to solve the problem. Regard the time growth rate as the derivative of the log. Solve, so you don't have the solution, you have the log of the solution, okay? Compute the exponential of, and you have the solution. Time for a break, and next a wider perspective on first order differential equations. Break, 15 minutes. We take a break, compute the exponential of, and you have the solution. Time for a break, and next a wider perspective on first order differential equations. Break, 15 minutes. We take a break of 15 minutes, and next we switch to the theory of first order examples of first order differential equations and the solution to the general model. let's do this. This is a new topic. And okay, let's do this. Okay, you have your slides about first order differential equations, but now, by the way, can you hear me? Is that okay? Is everything okay? I hope so.
Yes, we can hear you.
Okay, thank you. We start again. Let's do this. I'm introducing the solution to first order linear differential equations, okay? It's already written here, everything, every detail, okay? By the way, there is also some repetition, so just have a look at the slides. But what I'm doing now is to show you the same things in progress. So I hope that in this way you will resist a little longer to this new stuff. Okay, I'm showing the basic steps in progress because it's not difficult, but I understand that at the end of the week it can be mathematics on Friday may be not optimal for learning fast. Okay, so let me do this. Everything is already here, so don't worry about writing, okay? Just try to follow the development of the concepts. We learned how to solve this. Okay? I can also write this in this way. This is another way to write what we already know how to solve. So in general, the notation for first order differential equations will be like this, not minus r here, but a coefficient. So it will be like this. Okay? And more generally, and we know how to solve this, because this is x dot is equal to minus ax, which is basically this. So we know how to solve this. Now we have to learn this one. Not necessarily a zero, b number, constant here. So this is new. What we now are now going to learn, this is new, okay? But there is something which is even more general. Not necessarily constant, it may change over time. So this is a kind of exogenous component of the differential equation, which is in the basic model, it is 0. Now it will be 3, for instance, but then it can be evolving over time. And we will also learn this one. So next. And we may have a more general model in which also this coefficient is changing over time. Okay? I will only say something about this, but the techniques to solve this are just more complicated computationally, that are based on the techniques to solve this one. Okay? So this is the more general model of a first order linear differential equation. It is first order, and this is a general terminology, it is first order because only the value of the unknown function and its first time derivative appears in the equation. We may have more complicated equations in which you have a more complicated relation to be worked out between the first derivative, the value of the function, and maybe the second derivative also, okay? These are called second order linear differential equations, okay? We would have second order differential equations. So first order is because there is only the first derivative involved. Linear is because in the variable, in our variable, and in its first derivative, this expression is linear. It is our first derivative, or maybe a coefficient times our first derivative, plus something times our function is equal to something else, okay? AT and BT can be changing over time. They can be also non-linear. But if it is linear in x and x dot, as is the case here, it is a linear differential equation. So a non-linear would be x dot plus AT times x squared equal to BT. That would be non-linear, okay? It is linear. It is a differential equation, of course, so first order linear. And I would add also, in the general case, another adjective, which is important. This is the general case. If BT and AT are actually changing over time, this equation is non-autonomous. But if A and B are constant over time, the equation is autonomous. What is the meaning of autonomous versus non-autonomous? Look at the equation, which is autonomous. This is a number, for instance, 2, and this is, for instance, 3, okay? X dot is equal to 2x plus 3. Sorry, x dot plus 2x is equal to 3. The derivative of x depends only on the level of x. Okay? The trend of our variable depends only on the level at a given point in time of the variable. Whether this level happens at time 2, or at time 3, or at time 10, does not matter for the evolution. The evolution depends only on the level. Once you reach that level, you have that particular evolution. It doesn't depend on the specific point in time where that level occurs, okay? Look now at this equation, which is more general. X dot plus, for instance, 3 plus square root of t, x is equal to exponential of minus t, okay? Clearly, the derivative depends not only on the level of the variable, but also on what is the specific point in time where this level happens, okay? Because there is also a direct dependence on t. So non-autonomous means there is also a direct dependence on t. Here we don't have a direct dependence on t because the only dependence on t is through the level of the variable, okay? So autonomous versus non-autonomous. Autonomous equations, which is, I mean, the most part of equations in applied models are autonomous. They are also the easiest to solve or to understand the behavior, are autonomous. These autonomous equations have steady states. Non-autonomous equations generally do not have steady states, okay? Because there is also these parameters that depend on time. So it's very unusual to get a constant solution for these equations. Okay, autonomous equations have steady states. Also, autonomous equations can be of one variable, but also of two variables, can be easily represented graphically. Non-autonomous equations cannot be represented graphically in the space of the variables, because not only the variables matter, not only variable x matters, also time. So it's the graphical representation of non-autonomous equation is more difficult. So what is the, let's say, the usual way we present the solution to this one, which is our goal now, okay? This general first order linear differential equation of autonomous type, which means with constant coefficients. that do not vary over time. Okay, we solve the equation in this way. X dot plus AX is equal to B. The first step is, okay, I don't know what the general solution is, but my first question is, are there any constant solutions to this equation? Or steady state solutions? Everything is in the slides, okay? So don't worry. A constant solution is of the type xt equal to a constant, or C, I don't know, C maybe, K, water carrying capacity equal to C, for any t. Constant solution means like this. Among the family of solutions, there is something that goes like this. It doesn't change over time, okay? How would you find the constant solutions to this, if any, to this equation? We know that the solution must be constant, so its derivative must be identically equal to 0 for any t. This is identically equal to 0 means for any t, okay? Okay, so set this one equal to 0 for any t. The equation becomes like this, because our solution must satisfy the equation. But if we want to find out the constant solutions, its derivative will be 0, and this, by the way, this will be constant, okay? So what is the constant level x? Characterizing a constant solution in this case, okay? Our constant level x will be x is equal to b over a, okay? Is that clear? So the first step is to find constant solution. So now we don't have, let me see if everything is written here. Next, I switch to a particular example. Okay, that's right. The particular example would be this one. X dot plus 1 over 4x is equal to 2. Let me show you this. So in general, we don't know what the general solution is, but we know that there exists the possibility of constant solutions, and the unique constant solution to this equation is x star equal to a constant x star equal to b over a, where b is the term on the right-hand side and a is the coefficient of x on the left. Okay? By the way, it's clear that if b is equal to 0, the constant solution is 0. Do you remember the model of constant growth? The unique constant solution was 0, okay? Which is consistent with this one. So it's b over a. Example. Find the steady state solution to this one. X dot plus 1 over 4x is equal to 8. Sorry, to 4. Equal to 2, not to 4. This was the example in the slide, sorry. Equal to 2. Okay, so set x dot equal to 0. 1 over 4x is equal to 2. X star is equal to 8. Okay? By the way, if we start with x star equal to 8, and we imagine to run over time this differential equation, this becomes x dot is equal to minus 1 over 4x. Just move this to the right, plus 2. Imagine that we start with x0 equal to 8. So put x0 here. This computes the evolution in the next short time step, okay, intuitively. But if x0 is equal to 8, this term becomes 2, plus 2 is equal to 0, so the derivative will be 0. And our function will not move away from the value 8. because the time derivative is 0. What happens in the next short time step? Again, it is at the level 8. So this is again equal to 0. The derivative remains 0. And the function will, the trajectory will remain constant at the level 0. Okay, so this is the meaning of steady state solution. Now the next step is that of finding the solution to the general case. X dot is plus 1 over 4x is equal to 2 in our example. Next, we will see it in the general case. So we use this. In order to find the general solution, we just perform a change of variable. So why is it important to find the steady state first? Because next, we will change our variable. We will define another variable u, which is the deviation from x, the unknown function, and the steady state level. Okay? So we define a new variable u. Now, if the new, we have to transform the differential equation into one in the new variable u. What is x? I have x here is equal to u plus 8, right? I will replace 2x u plus 8. Next, what is x dot? Sorry, u dot. The time derivative of u is x minus a constant, so it is equal to x dot. Okay? Replace u dot, which is equal to x dot, plus 1 over 4. X is, this is x, of course. X is equal to u plus 8, equal to 2. What happens here? That this part, 8 divided by 4, becomes 2. So we can eliminate this, and the 2 on the right. So it becomes u dot plus 1 over 4u equal to 0. Can you see the point? The main point of the... So basically, if we rewrite the equation in terms of the deviation between the variable and its steady state level, we get an equation which is this one. U dot plus 1 over 4u is equal to 0, right? Because the other term was 2 plus 2 equal to 2 on the right. It becomes equal to 0. And this is the constant growth model. U dot is equal to minus 1 over 4u. So we know what the general solution to the constant growth model is, u of t, but remember that u of t is not the variable, it's the deviation between the variable and the steady state. U of t is equal to a constant times exponential of minus 1 over 4t. Okay? Now replace again to u its definition, xt minus 8. We get xt minus 8 is equal to a times exponential minus 1 over 4t. Finally, xt is equal to a times the exponential minus 1 over 4t plus 8. This is the general solution, but there is a constant a here. We have to specify the value of this constant by adding an initial condition. If we add an initial condition that x0 is given, which is the boundary condition is generally an initial condition, we want a specified level for the initial level of our variable. So now, what is x0, which is equal to x0, because we impose this, on the other hand, must be equal to what? A times z times 1, because 0 here is 1, a plus 8. It follows that a is equal to x0 minus 8. Here is the interpretation of a constant a in the solution. Finally, the solution 2. this is a summary of what we found. The solution to this first order differential equation, x dot plus 1 over 4x equal to 2. With this initial condition, subject to or corresponding to x at time 0 given, this means the value of the trajectory at time 0, and this is our given value. For instance, 2, 10, 4 is xt is equal to what was a was x0 minus 8 exponential minus 1 over 4t plus 8. Okay? And this has a very interesting interpretation because, so in general, now remember that our a lowercase a, the coefficient was 1/4. Here we have minus a, okay? And this 8 here is p over a, okay? So in general, we have xt is equal to x0 minus 8 was the steady state, x star. X star is equal to p over a times exponential minus at plus the steady state itself. Okay, so this is from the example. This one is the solution to the general form x dot plus ax equal to b with x at time 0 given. Clear? Now, this is the solution. And the solution has an important structure which is common to many models. Look at the structure. The solution is made up of a constant part and a time-varying part. The constant part is the steady state component of the solution. In many models, we call it the long-run component of the solution. But the time-varying part is a part that adjusts over time, of course, and it is given by the initial deviation from the steady state solution, also from here, the initial deviation from the steady state, multiplied by a coefficient. This coefficient, over time, decreases and tends to 0 if a is positive, so that minus a is negative. But if a is negative, if we have minus 1/3, for instance, and we move it to the right, becomes plus 1/3, so the exponent appears with a positive coefficient, the initial deviation from the steady state grows over time, okay? So in this case, it decreases over time. But in the general, if it is positive, it grows over time. So when a is positive, the transitory component shrinks, decreases, and disappears over time. If a is negative, the transitory component becomes larger and larger over time, okay? So basically what we get in the example is this. Our solution has a long-run component, which is at the level 8. Okay, this is t. This is xt as specified by our expression. Suppose that x0 is here. This is very similar to the carrying capacity model we saw before. X0 is here. So this is the initial deviation from the steady state, which is x0 minus 8. Actually, if you measure it, this is 8 minus x0, okay, so this is the negative of this one, but it is multiplied by exponential of minus 1/4 t, so this decreases over time, the deviation decreases over time, okay? And in the long run, what is left is the steady state level. What happens if we start above? The same, because if we start above, for instance here, we have now a positive deviation from the steady state. In this case, we have a negative deviation. Here we have a positive deviation, but anyway, it is multiplied by something that goes to 0. So in the long run, we have this, okay? So if you look again back to the formulas here, like this, you see that it doesn't matter whether x0 is larger than 8 or it is smaller than 8 in this model, okay? If it is larger than 8, you start with a positive deviation from the steady state. If it is smaller, you start with a negative deviation. It is below. But anyway, this deviation tends to disappear in the long run. And what is left in the long run is 8. This is the case of, clearly, a model that goes to some equilibrium in the long run, okay? But if A, this parameter, is negative here, you move it to the right, it becomes positive. This means that your exponential term has a positive coefficient here. So this part will grow over time. So for instance, if we have a solution like this is a case in which we can represent something like this. Okay, suppose that you have a steady state here, which is x star, maybe 8, I don't know, it depends on the parameters of the model. And you have something like this. The solution xt is the general, is the particular solution we found above, is equal to x0 minus x star times exponential of minus 8t, but now a is negative. Okay, so minus a is positive, plus x star. So, plus x0, sorry, plus x star. Okay, now this is a growing exponential factor over time. So suppose that you start with a very small deviation, x0 is here, what happens in the long run? And this deviation will become larger and larger and larger. So you will have a solution that goes like this. If you start above, the same. You will have a solution which is positive, even very small initially, but it is multiplied by a growing exponential factor, and it goes like this. So there is still a constant part of the solution, which is the steady state, but this is not what you will get in the long run. It is just a constant part, but the deviation from this equilibrium level will grow forever. So this is the idea of the family of solutions, okay? So here we have a family of solutions that goes like this, depending on the initial level of x0, okay? It is very similar to our constant growth model, where now the role which was played by the x-axis is played by this horizontal line, okay? In the constant growth model, this was played by the x-axis. And this is the case of the constant growth model where we have an actual growth, okay? So minus a is positive, and we have something that goes like this. So the family of solution is this, depending on what is the initial deviation from the steady state. So basically, this is just the constant growth model shifted upwards or downwards, depending on where is the location of this constant level. Maybe positive, maybe negative. Some others have a negative steady state solution. So there is nothing conceptually different. And in fact, we have a solution which is basically obtained by just changing the variable in terms of deviation from the steady state. So this is the basic idea. So everything is explained here, including the example. So you don't need to write anything. Now let me see more examples. There is also the general case here. Now let me specify a particular solution. We know how to specify a particular solution by leaving x0 as a parameter, but we can do that also numerically. So if we have our previous solution by leaving x0 as a parameter, but we can do that also numerically. So if we have our previous, this is already written in terms of the desired initial level of the variable, but maybe you may want to start from a general solution and then specify an initial condition numerically. So you may want to do this. So basically you have your general solution, which was xt equal to, was a times exponential minus 1 over 4t plus 8, right? Suppose that you want x times 0 equal to, your x0 is equal to 3. So you write here x at times 0, which is equal to a plus 8. This must be equal to 3. And this means that a must be equal to minus 12, okay? Minus 11, sorry, I'm really tired. So differential equations, but I cannot compute the value of a that satisfies this equation. So it's equal to minus 11, okay? So minus 11 plus 8 is equal to 3. So this means that our solution will be xt is equal to a 8 plus, minus 11 times the exponential minus 1 over 4t, okay? No, that doesn't work. This is, look, I'm really tired. Please stop me when I start doing that. It is 5, of course. So a plus 8, it is minus 5. A plus 8 is equal to 3, so a is equal to minus 5. But everything is recorded, you know, so it's really, I'm really happy. So minus 5 exponential minus 140. So this means that you can check your solution, I mean, because suppose that you solve a differential equation with a specified initial condition. First of all, let me check that my solution is correct. We have to check two things. First, our solution satisfies the differential equation. Second, it corresponds to the initial condition that we impose. Is this solution actually consistent with the initial condition that we imposed? Okay, what is x at times 0? Times 0, this becomes 1. 8 minus 5 is equal to 3. Okay, it is consistent with the initial condition. But the second point is, how can we check that our solution to the differential equation is correct? Because when you have an algebraic equation, you find a numerical value, you put the numerical value into the equation, and it must end up with the left-hand side equal to the right-hand side, okay? This is for an algebraic equation. What about a differential equation? Just rely on the definition. What is the differential equation requiring in this case? We must have that x dot time derivative plus 1 over 4x is equal to 2 for any t. So put here your solution, put here the time derivative of your solution, put here your solution, and the left-hand side must be identically equal to 2. So what is the time derivative of our solution? We know that our solution that we found, xt is equal to, takes time, xt is equal to 8 minus 5 exponential minus 1 over 4t. Okay, what is its time derivative? X dot. X dot is the time derivative, so it is 8 is a constant. So minus 5 times time derivative is minus 1 over 4 exponential minus 1 over 4t. Okay? Put the time derivative here. Put your solution here. So we have time derivative minus 5, so plus 5 over 4, basically. Exponential minus 1 over 4t, plus 1/4 times x, x is here, 8 minus 5 exponential minus 1 over 4t, must be equal to 2. Let me check this. Okay, here we have plus 5 over 4 exponential minus 1 over 4t. Look at this, it's minus 5 over 4 exponential minus 1 over 4t. Okay, so this and this are one the negative of the other. What is left is 1 over 4 times 8 must be equal to 2, we know here. In fact, it is equal to 2. Identically. Identically means for any t. What we found doesn't depend on t. At any point in time t, actually our function satisfies this property. If you take the derivative of the function and you add 1/4 of the level of the function, you get exactly 2 at any point in time. So this is the way we check the validity of our solution. Now remember that what we do here, which is in principle relatively easy, is a way to check the solution in other cases that are more complicated. For instance, the case in which our B, our 2 here, changes over time. So in that case, solution must be more complicated. You may want to check the solution, but also sometimes we impose that the solution is satisfied because we have to find a constant, which is called the method of undetermined coefficients that we will see. You find the solution, but you have to specify a constant. You can specify this constant by imposing that your solution is correct. We saw that once in the case of integrals, you remember. We know the general structure of the integral, but except for a constant, and we find the constant by the method of undetermined coefficients. So by imposing that the derivative is equal to the given function to be integrated. We can do the same here. We find a solution, we are not sure about a constant, we impose that it satisfies the differential equation, we find the precise value of the constant, okay? This is a very general technique which is called the method of undetermined coefficients. Okay, so this is basically the way we check the solution. Now, we're almost done. The last thing I want to do is just to show you that our previous model of growth towards an upper limit is just an example of a differential equation of this type. It's just written in a slightly different manner, but it is an example of a differential equation of this type. It is in the next 2 slides, but I'm going to write this here in 2 minutes. So the growth towards an upper limit is just an example of a linear first-order autonomous differential equation. So this is a particular case of our general model. I don't really remember the data of our previous example. You may help me. X dot was equal to, let's say, 0.15 times 1000 minus x. Is that right? Okay, so why is it a model that corresponds to our general model, x dot plus ax is equal to b, right? Because you can write this in this way, x dot is equal to 0.15 times 1000 minus 0.15x. So in general, this is x dot is equal to a times k minus x, right? This was the general equation. So x dot is equal to 0.15 times 1000 minus 0.15x. Now move this to the left. X dot plus 0.15x is equal to 0.15 times 1000, okay? So basically this is our B, and this is our A, our new A according to the notation of this model. So you can solve it also with the solution formula for the general model, okay? First, find the steady state. What is the steady state in this case? It is the carrying capacity, we know that already. But let me find the steady state by using the formula. The steady state x star is equal to b over a, so b is this, a is this, so it is equal to 1000. And the solution is just xt is equal to capital A, which is the multiplicative constant, times exponential of minus 0.15 t plus 1000. Okay? So what is capital A? If we impose an initial condition, x at time 0 is equal to x0. So x at time 0 is a plus 1000, and this must be equal to x0. So basically, A is equal to 1000 minus x0, okay? Is that correct? Xt is equal to A times exponential minus 0.15t plus 1000. Yes. Yes, it is. So let me do that. So this x times 0 is equal to a plus 1000 and this must be equal to x0, which we impose. So a is equal to x0 minus 1000. More generally, a is equal to x0 minus the carrying capacity. And if you look at the solution formula that we found for the growth towards an upper limit, if you look at the solution formula, you see that it is the same because we had a minus sign here. So carrying capacity, 1000. Here we have minus k minus x0. In my solution, I have plus x0 minus k times exponential of minus 80, okay? Which is exactly the same. So xt is equal to, replace to a, this one. It is equal to x0 minus 1000 exponential minus 0.15t plus 1000. So it is equal to x0 minus 1000 times exponential minus 0.15t plus 1000. And when we solve this as a particular mode, previously we got 1000, which was k minus, now there is a minus here, so it is 1000 minus x0 times exponential minus 0.15t, which was in our formula minus k minus x0 exponential minus 18, okay? This was the solution formula of the growth towards an upper limit. It's clearly a particular case of this model. It is just expressed differently, in a different manner. But it is of the type x dot is equal to x dot plus ax equal to b. X dot plus ax equal to b. Anyway, everything is here, okay? So here in the last slides here, I show you a constant growth model like the one we solved before. I show you that actually the steady state is K, which is the carrying capacity. And actually, if we write down the solution using the general formula, we get the solution, the same solution of the constant growth model studied before, okay? So the growth towards an upper limit in its most naive version is a particular case of a linear autonomous first-order differential equation. Okay, so this is basically the theory of the solution of linear first-order differential equations. Okay, so next time I will show you how the solution changes if we have a time-varying B, how we can find the solution in this case, and we will see also more examples of this. This reduces to applying a very simple formula. The important thing is understanding the meaning of the formula, okay? A constant component and a time-varying component. If we are lucky, the time-varying component vanishes over time, okay? And everything goes to the equilibrium, to the long-run equilibrium, which is the steady-state part of the solution. Otherwise, it explodes away from the steady-state equilibrium level. Very simple. We will see more examples just to see more numerical examples of this model, but it is really simple. What is slightly more difficult is the case in which we have a time-varying B, which we will learn how to solve. Okay. Thank you. See you next week. Goodbye.
Bye.
Bye.
Thank you, bye.
Have a nice weekend.
You too, thank you.